So here we'll make a force analysis of a single cylinder engine. So this is the connecting rod, this is the piston, and this is the crank, and this is the bearing for the bearing center line for the crankshaft. So from this is a small end, the small end to the center of mass of the connecting rod, small a, and from the center of mass to the big end, small c. You can also draw it vertically. So this is the figure actually. This is the crankshaft. So the crankshaft is like this. This is the crankshaft, and this is the connecting rod. This is the bearing. This is the bearing for the crankshaft. This is the piston. This is the connecting rod, and this is the cylinder. So now here we have shown the piston, the connecting rod, and the crank. So and there are four forces of interest, four types of forces of interest. One is the gas pressure, and another is the inertia force on the piston, and correction torque and weight of the connecting rod. So actually we'll assume that this crank, connecting rod, piston to be static, and the forces due to acceleration are acting on it as inertia forces, and will consider it as a problem of statics. So here we'll consider the inertia force acting on the system due to several types of acceleration, that is linear acceleration of the piston, angular acceleration, linear acceleration of the piston, angular acceleration of the connecting rod, etc. So here we'll consider four types of forces: the gas pressure, inertia force on the piston, correction torque, and weight of the connecting rod. And for these four types of forces, we'll find out what are the forces coming on the supports, and we'll superpose to get the total force and total torque. Also we'll find out what is the torque coming on the crankshaft. So these are the four types of forces. So and we'll assume the crank, actually, as we have seen in our previous lecture, that this crankshaft is executing general plane motion, but we'll divide it in two parts, one at this, one at here, and the other at here. So this part executes pure linear motion along a line, and this part rotates about this axis as a particle placed at the crank tip. And though it is the MA by MC by L and MA by L, but what is done is as an approximation. So 1/3 of the total mass of the connecting rod is placed here, and 1/3 is 2/3 is placed here. So 1/3 mass is placed at the piston end or small end, and 2/3 mass is placed at the crank tip. So and due to that the correction torque is coming. So we'll also find out due to this correction torque what is the torque coming on the crankshaft, and due to the inertia force on the piston accelerates. So we'll put inertia force on, since the piston accelerates, so this AP is the acceleration of the piston. So due to that we'll put an inertia force on the piston, and due to that inertia force we'll find out what is the torque coming here, and also the force coming here, and we'll find out the reactions and the reaction forces and the torques also. So let's see. So first we consider the gas pressure. So this is the gas pressure acting on the piston. This is coming from the cylinder on the piston. The reaction N1. This is phi. This is theta. This is the length of the crank R. This is the length of the connecting rod L. And this is the torque T1, which is coming due to PA, and this is N1, which is coming on the crankshaft from the bearing. So this is this T1 as if we are holding the crankshaft. So this T1 is coming due to that, because we are considering it as a problem of statics and someone is holding the crankshaft and preventing it from rotating. So due to that, this T1 is coming and N1 is going to the bearing of the crankshaft. Yeah, and also some R is coming. So here I made a mistake. N1 is not going to the bearing. N1 is coming on the crankshaft from the bearing. So this T1 is acting on the crankshaft from the load, and this N1 is acting on the crankshaft or on the system we are considering, and it is coming from the bearings. So on the bearings the opposite force will go, and here this R1 is also coming from the bearing on the crankshaft. So this R1 is going to the structure which is holding the bearing. So just try to understand this Fg is P into A is coming due to gas pressure. This is coming on the piston from the cylinder. This N1 is coming on the system shown from the bearings which hold the crankshaft. This is T1 is coming on the system we are showing, that is the crankshaft here, from the load, and that means this torque is actually holding the crankshaft here as if, and this is R1 is coming on the crankshaft from the bearing, and this R1 is going on the bearing and from the bearing to the structure holding the bearing. So this can be this is actually a point mass here joined by a rigid link, massless link. So it is a two force member, and this is the force P, this is PA, and this is N1. So under these three forces, this is a system of concentrated forces. This is under equilibrium. So Fg equal to P cos phi, so and P sin phi is equal to N1, and this N1 is actually T1. So T1 is N1 multiplied by L cos phi plus L R cos theta, and T1 is actually, if you look at this, look at the crankshaft, then P is coming from the connecting rod. So, and this is T1 and this is N1, this is R1. So these are the forces acting on the crankshaft. So the torque about O is T1, which is actually equal to this P into this perpendicular distance OQ, this perpendicular distance OQ, and OQ can be shown to be, so this angle is phi, because this angle is phi, so this angle is also phi, this angle is theta. So this is R. So if this is phi, then this angle is also phi, this angle is also phi. So theta plus phi, so R sin theta plus phi, R sin theta plus phi is OQ. So P into R sin theta phi, theta plus phi. So P is Fg by cos theta, which we have seen here. P is equal to Fg by cos phi into R sin theta plus phi. So sin theta cos phi plus cos theta sin phi by cos phi. So this is sin theta cos phi goes plus cos theta tan phi. So Fg r sin theta plus r cos theta tan phi. So what is r cos theta tan phi? This is r. So r cos theta, r cos theta, r cos theta is r cos theta, r is this much, cos theta into tan phi. So r cos theta tan phi, r cos theta is this much, tan phi, this is phi. So r cos theta tan phi is this much, and r sin theta is this much. So r sin theta plus r cos theta is this much, and r cos theta tan phi is this much, because this angle is phi. So this plus this, so this is OM. So Fg into OM. OM is just the vertical line from passing through O, and uh, and M is the point on the extension of the connecting rod. So just you extend the connecting rod and you find out the intersection of this vertical line with this connecting rod, and that point gives you the M, and Fg into OM is the torque coming due to the gas pressure. Okay, so this R1 is going on the structure, and since see in the due to firing in the cylinder, PA is coming here and PA is also going on the cylinder. So if you see this figure, so PA is coming on this face and PA is also going on this face. So this is the structure holding the cylinder. So PA is coming here, and from these two bearings again R1 is going on the structure. So R1 is going on the structure and PA is coming here, and R1 is equal to PA. So there is no net force on the structure. Now for the inertia force, you see, since this is accelerating with AP, since this is accelerating with AP, so since this is accelerating with AP, which is x double dot, we are showing an inertia force F suffix I here. So here the reaction is N2. Again the corresponding torque is T2, which is holding the crankshaft. R2 is coming on the crankshaft from the bearing, and this R2 goes to the structure holding the bearing. So this goes to the structure. But here you see this is coming, this is due to the motion of the piston coming on the piston, but it is not coming on the cylinder. So it is not coming on the structure at this end. So Fi is not acting on the structure, it is only whereas we are taking it to be acting on the piston, but R2 is acting. So R2 is the unbalanced force. Here you see, here PA we are getting and R1 we are getting, but here on the left side we are not getting anything, because Fi is only due to the motion of this. Fi is not acting on the cylinder, but R2 is acting here. So this is the unbalanced force is acting on the structure, and here T2 is Fi, so minus Fi OM, because it is in the other direction. So Fg is in this direction and Fi is in the other direction. So T2 is Fi into OM. OM as usual, if you extend this, the point where it cuts the extension of the connecting rod, extended connecting rod. So this OM can also be shown to be Fi can be shown to be Mr. Mr is the total reciprocating masses, which is the mass of the piston plus 1/3 mass of the connecting rod. Omega square r cos theta plus cos 2 theta by n is the expression for acceleration. So Mr into acceleration, which is the inertia force, multiplied by OM. and here N2 multiplied by R cos theta plus L cos phi is equal to T2. So here we need to balance this Fi actually, because this is the unbalanced force. The unbalanced force on the structure comes due to this inertia force. Now we have seen the correction torque acting on the connecting rod, because we have divided it in two masses, one at the piston end and one at the crank tip. So here, so N3 into L cos phi plus R cos theta is equal to T3 plus Tc, one equilibrium equation, the moment equilibrium equation. And here if you consider the free body diagram of the connecting rod, so there is N3 here, and if you consider it as P, then your this Tc is P into L cos phi, or P is Tc by L cos phi. This P is same as N3, and if you now consider the crank which is here, so this is the crank, so P is coming here, so this is T3, this is N3, N3 should be equal to P, and T3 is P R cos theta. So this, if this is P, so P R cos theta is T3, and this P is actually Tc by L cos phi. PR is Tc by L cos phi. So this is T3, the torque coming here at the crankshaft center due to the correction torque. So now you can just replace phi by theta using the relation. So sin phi is sin theta by n. So this is 1 minus sin square phi. So sin square theta by n square, and this is actually the torque. And you know the correction torque expression is this. This is the mass of the connecting rod. Phi double dot is the angular acceleration of the connecting rod. A is the distance between the small end and the center of mass of the connecting rod. Small l is the length of the connecting rod, and capital L is the distance of the center of percussion from the small end. So now this is actually Tc. Now put the value of Tc here to get T3, and this is due to the weight of the connecting rod. This is simple. So weight of the connecting rod, so parallel forces. Now you know what is P1 and P2. P2 is A W by L, and here this P2 is actually P2 multiplied by R cos theta. So here it should be actually, so this is A cos phi. No, it's okay. Sorry. So AW by L, because A is this length and L is also along this. So it's okay, AW by L, and AWC, that is the weight of the connecting rod also, you can make it. This is the weight of the connecting rod. So AWC. So here AWC. So here this is the torque coming due to the weight of the connecting rod. So now you can superpose this and get the total torque coming on the crankshaft. So now if you superpose these four torques and you plot it versus theta, then the diagram theta is the angle of rotation of the crankshaft, and if you plot that, that is the turning moment diagram. So if you think of a 4-stroke engine, so just in 1/4 of the whole cycle there is one power stroke. So you can understand the turning moment is not cannot be constant. The inertia force also changes. The gas pressure is just cannot is not constant, it is varying, and the inertia force also changes. So this is the turning moment diagram, and so from the superposition of the torques we get the turning moment diagram, and from the acceleration of the piston we get the unbalanced force, and if it is a multi-cylinder engine, then the unbalanced force from all the cylinders they create moment. So that is another case which we will study. So from here actually two topics originate. One is the balancing part and one is the turning moment diagram, and since the turning moment varies, there is a question of using a flywheel. So we'll look into both of these topics in our subsequent classes. So for the time being we stop here.